Hi everyone, today I'm going to walk you through from start to finish a binary classification model I trained in Google Colab to predict whether a person is likely to have diabetes based on survey response. The target variable in this project is diabetes binary. A value of 0 means no diabetes, and a value of 1 means diabetes. By the end of this workflow, the model outputs a risk probability for each person in the test set, and we package those predictions into a submission file. To begin, it is important to understand the data challenge we are working with. This data set is class imbalanced only with about 13.7% of training sample are positives, which shows here also in our result. That matters because if we only look at the accuracy, we could get a deceptively good number even with a weak model. For example, a model that predicts no diabetes for everyone might still achieve a seemingly decent accuracy simply because most people are in class 0. So instead of relying on accuracy, we elevate performance using metrics that better reflect real-world usefulness under imbalance. Specifically is ROC, AUC, and PRAUC and F1 score. With that text in mind, I will explain end-to-end workflow. The first step is loading the data. We read the training and the test files, and we confirm that training files contain the target column diabetes binary. Next, we adjourn the feature columns with training and test data. This step is crucial because the model can only make the test predictions if the feature set is consistent. So we keep only features that existing on both files. After adjourn features, we handle data quality issues. Especially missing values, we use median imputation, which means any missing value in feature is filled with the median of that feature in training data. The median is a stable choice because it's less sensitive to outliers than the mean and it ensures the training process does not break due to non-values like zeros or blank. Once the base features are clean, we add a small amount of features engineering to help the model capture risk patterns more effectively. Instead of feeding only raw variables, we create a few additional features that summarize meaningful relationships. For example, we include interaction style signs such as BMI times age and combined with health indicators that compress multiple related variables into a single risk pattern input. The goal here is not to overcomplicate the dataset, but to give the model clear signal for common risk structures. Next, we create a reliable evolution setup. We split the training data into training portion and a validation portion using stratification, which ensures the positive to negative ratio stays similar in both sets. This is important because we want the validation result to reflect the real distribution. We also apply scaling as part of a consistent pre-processing pipeline, particularly because it benefits linear models and keeps the process uniform across different model types. At this point, we address the biggest modeling challenge, imbalance. Instead of assuming one approach is best, we evaluate two training settings. The first is original, where we keep the natural imbalanced distribution. The second is mode, where we oversample the minority class by creating a synthetic positive example to balance the dataset. Importantly, we treat this as an empirical question, SMOTE, SMOTE. Sometimes helps, but it can also introduce noise. So we compare both settings using the validation metrics rather than guessing advance. Now we come to model training and comparison. We test three representative model families to cover different assumptions and strengths. The first is logistic regression balanced, a class-weighted logistic regression model that serves as a fast interpretable baseline. The second is extra trees, a tree ensemble model that can capture nonlinear relationship and feature interactions. The third is LightGBM, a gradient-boosted decision tree model that is typically very strong on structured tabular data. By comparing this model under both original and SMOTE settings, we can identify which combination generalizes the best. After training and evaluation, the output identifies a clear winner, like GBM trained the original distribution, when results that the best setup is like GBM. It means that keeping the real-world imbalance actually produces the best validation performance. This also tells us that for this dataset and configuration, SMOTE did not provide a consistent advantage. That outcome is not unusual. Tree-based models can sometimes learn artificial patterns from synthetic over-sampled data that do not transfer as well to real distribution. To interpret the model performance in a meaningful way, we focus on what each metric actually implies. First, ROC-AUC, which around 0.822 indicates strong ranking ability. In particular terms, if we random select one person who is truly positive and one person who is truly negative, the model assigns a higher risk score to positive person about 82.2% of time. That is strong indication of overall discrimination. Next, PRAUC around 0.416 is especially important here because positives are rare. PRAUC helps answer the question, when the model flags someone as high risk, how trustworthy is that signal? A value like 0.416 shows the model is meaningfully better than chance at concentrating true positive near the top of its risk ranking, which is exactly what we want under imbalance. Then F1 around 0.467 describes performance after turning probabilities into hard labels. F1 balance precisions how many predicted positive are truly positive against the record how many true positive we successfully capture. In plain terms, This metric reflects how well the model manages the trade-off between missing high-risk individual and risk too many false alarms. The trade-off is controlled by the sharehold in our run is about 0.605. The model output probabilities, not direct yes or no answers, so we choose a cutoff. If a predicted probability is greater than or equal to 0.605, we label the person as high risk, which is 1. Otherwise, we label them as a low risk, which is 0. A higher sharehold makes the model more conservative, producing fewer positive and typically higher precisions. A lower sharehold catches more positive, but also increases the false positives. Reporting the sharehold makes the decision rule explicit and interpretable. Another practical check in the output is the prediction distribution. How many test cases are predicted as 1 versus 0? This matters because it helps us spot unrealistic behavior. If model predicts almost everyone as 0, it may be too conservative or sharehold could be too high. If it predicts too many, it may be overly aggressive or sharehold too low. Comparing this distribution to the training positive rate helps confirm that the model output is reasonable range. Now beyond the metrics, we also need to interpret what kinds of features drive the model's predictions. It is important to clarify that what I'm describing here are predictive associations, not causal conclusions. The model learns patterns that correlated with diabetes risk in the training labels, but also not prove that many single features causes diabetes. With that in mind, one major group of predictors is physiological and chronic condition signals. Features such as BMI, high BP, high calories, and age often carries strong predictive information. Higher BMI is commonly associated with insulin resistance risk, and high blood pressures and high cholesterol are frequently linked to metabolic syndromes and cardiovascular strain. Age also captures accumulated risk over time. In addition, history indicators like heart disease or attack and stroke can reflect long-term vascular and metabolic burden. Light BGM does not rely on these features individually. It excels at learning interaction patterns such as when several of these risk indicators appear together. A second predictor group relates to lifestyle and behavior, which often represents the multiple risk. Variables such as physics activity, fruits, veggies, smoker, and heavy alcohol consumption describe long-term habits connect to overall health risk profiles. For example, low physical activity is often associated with higher metabolic risk, and dietary patterns can reflect broader health behaviors. This factor allows the model to capture risk structures that are not purely clinical but still statistically informative in population dataset. The third group involves self-reported health status and functional elimination, which can act like early warning signals. Variables like general health rating also, along with physical health and mental health and functional indicators such as different work can reflect persistent health burdens. In many cases, people who report consistently poor health status may share underlying chronic condition risk patterns. The model used these signals to strengthen its overall risk assessment. Finally, the dataset includes healthcare assets and screen signals such as any healthcare, no doctor cost, and a chronic disease check. These features may not directly cause diabetes, but they often influence whether conditions are detected early, whether preventive care is accessible, and how chronic risks are managed. In survey-based population data, those patterns can still predictive of observation outcome. To conclude, the most important way to interpret this model is to see it as producing a risk probability, not a medical diagnosis. A higher predicted probability means the person's feature patterns resembles those labeled as predictable diabetes in training data. This makes the model useful for the risk screening and prioritization, especially in public health to prevent contacts. But it does not replace the clinical testing or any professional medical evaluation. Thank you.